Good morning. And welcome. Thank you for joining us to hear our talk about pragmatism, which is rampant at Starling Bank. By way of introduction, Starling was founded by our CEO, Anne Bowden, in 2014 in reaction to the banking crisis, and believed and continues to believe now that customers need to be treated fairly, to be empowered, and that building a bank on modern technology is the best way to achieve this. Martin and I started within about a month of each other 4 years ago, as then of a very small team, just two of a couple of engineers. And I'm now practice lead for web technologies, which makes me responsible for anything that runs in the browser and how it gets there, ideally quickly and securely.
And I'm Martin. I'm engineering lead for core banking, where I deal with services at the heart of the bank, involving finance, treasury, credit, fraud. And to achieve Anne's mission, Starling has always been a really customer and delivery-focused organization. And that has translated into a pretty pragmatic engineering culture. Dan and I, we sit at sort of opposite ends of the technology stack, but we thought it would be really interesting to talk to you today about actually how similar many things are across those two different areas if you dig a little beneath the surface. So we're going to start by talking with some ideas, some theory. We'll talk about complexity, a bit about relational modeling, functions, projections, and that will mainly give us a bit of a language to help explain how we think about our systems. And then we're going to use that language to describe a couple of slightly more practical examples. There's the web guy over here. He's going to talk to us about how that theory applies in the web stack, and I'm going to try and do the same in my neck of the woods, talk about the banking ledger and how we push data around our platform. And then we'll sum up by talking a bit about some of Starling's engineering principles. So I want to start off by talking about complexity, to think a little bit about what makes building systems difficult, and what makes that difficulty become harder the longer you are building these systems. And the distinction I want to introduce was suggested by Fred Brooks in a very famous 1986 paper called No Silver Bullet. It's the third time I've seen that up on slides at QCon this year. The bit we're interested in is the subtitle, which is Essence and Accident in Software Engineering. And so Brooks distinguished between essential tasks. The essential is the system that you're building as it exists in a sort of idealized world. If you didn't have to worry about the technical constraints, what of your system would be left? It's a form of complexity that you can never remove, or you would be left with no working system at all. It's the data and it's the logic at the heart of the system, and it's declarative. It's the what, not the how. On the other hand, the accidental is how you get that system running. Whether you're poking holes in a punch card, writing assembly code, or deploying an EC2 instance in AWS using CloudFormation. Accidental is definitely a slightly odd word here, but what Brooks is trying to get us to think about is how much time and effort are we spending defining what the software should do for the customer, solving real problems, versus persuading a machine to push some bits around to actually execute that stuff. And we can think of complexity as a sort of a spectrum. On the left, we have the core of the system. We can never remove it. As I say, it won't do anything useful. The system won't do anything useful without it. And we can divide that into state or data and a wrapper of logic or business rules. And as we move to the right, we can think about accidental complexity. And without the accidental part, the system won't execute. So a certain amount of that we classify as useful. We almost certainly need it to build a useful and a performant system. However, we want to make sure we don't drift too far along into the useless complexity. That adds no value to the system, but it has lots and lots of costs. And it can take on at least two forms. We can talk about underinvestment in our system, might cause us to expend a load of effort on boilerplate, on wrestling abstractions that are no longer fit for purpose. And on the other side, maybe there's overinvestment or over-engineering our systems. We create these high upfront build costs, probably some long-term maintenance in the hope of some future gain in productivity. And as you move along the spectrum, you have to ask the question, like, how much accidental complexity are you willing and able to give to accept given your particular context, given your business, given your strategy, given the stage of your growth. And perhaps we can think of pragmatism as avoiding some of the temptations that lurk to the right side of this spectrum, choosing and moving with care. So what exactly is essential complexity? What does it look like if you're actually building systems for a living? Dan and I love this quote from Rich Hickey, the godfather of closure. It doesn't really matter what language you use, data is really the foundation of the system. And for many of us who build data-centric systems, we would argue that you can think of essential complexity as more or less as data modeling. There'll be lots of other things to consider. Shortly, Dan will go into some of them. But for now, we can think of modeling the data our system will store as actually the best way of getting to grips with that essential complexity. It's an effective tool for the team to think through the problems it faces. And what I'm really talking about is a team standing around a whiteboard drawing boxes. It's a focus on the domain, gives us half a chance of actually sharing a discussion about the problems that we're solving. That effective communication is obviously essential. So finding this clear, simple syntax, whatever it is, allows everyone to contribute to the discussion, to challenge, to improve the solution, no matter what level of expertise. And I acknowledge this is really, really simple stuff. But when as a community we spend so much time focused on the complexity of our cloud deployments, on the subtleties of your favorite programming language's syntax, it does serve occasionally to remind ourselves that at the core, this is a job about creative thinking, about finding simple mental models to understand the problems that we are solving and the solutions. And once you have those, we'd argue that quite a lot of the code actually kind of writes itself. And so the team keeps talking, challenging this model we've come up with. I like to think of sort of flexing the model as you're looking at it, stretching it to see how it responds to a bit of strain from a few different angles. Imagine how it would handle some future requirement. Think about scenarios maybe where a cardinality you've drawn on the board might no longer make sense if we introduced some new concept. So you're trying to identify concept entities that you might have missed or conflated. And we think really carefully about time. So we're drawing this as a snapshot, but the data you're stored is stored over a period of time, it arrives over a period of time. And so you'll probably want to ensure also that as you look back on the system, you know what state that system was in. You can reproduce it. You can and you should often store event model data in a relational database. You don't need every entity to share the same generic data type to store an event-based model. And it might feel a little bit like upfront design. You're spending quite a lot of time on this stage, but the cost of iterating at this point in the process is so cheap. It's like a form of really efficient prototyping. And the idea is obviously not necessarily to support all those future requirements. We don't even have to create all the tables. The thing is to think deeply about the problem. And I'm not going to ask any interview questions about Boyce Cod, but what I'm really talking about here is the process of normalization in relational database design. Questions that you ask yourself in the hope that the model might survive a little bit of future change. When Edgar Cod described relational modeling in this 1970 paper, he advocated for this concept of data independence. It's a clear separation of the application program from the physical representation of the data it's accessing on disk. And described this problem of access path dependence. So it's a problem we still see today all over the place. So document databases are really useful in many contexts, but the code that operates against them needs to have a pretty intimate knowledge of the structure of the data as it sits in the database, and probably the structure of many versions of that data. If you're updating on read, for example. REST APIs have a similar property. Note the popularity of talks on GraphQL appearing now at QCon. Even breaking a system into microservices. In each case, you're forcing yourself to collapse this multi-dimensional space down along a single dimension, which you happen to deem more important than the others at that point in time. And inevitably, there will be other contexts, and we'll wish in those contexts that we'd chosen a different dimension. So the key thing here is to think about is that the data is stored without the knowledge of the path from which it is accessed. We're pulling that out of the data itself so that we can add it back in other parts of the system where we think it's more appropriate. We use Postgres as our relational database management system. With Postgres, we've started to move along the right of that spectrum beyond the essential data into the essential logic and even into the accidental. And SQL gives us this data independence. It's that declarative language through which we can choose on a query-by-query basis which dimension or which access path we want to pick for the data. And it lets us define constraints, which is incredibly important for us. It allows us to create this sort of declarative barrier. Facts are only stored if they are true according to the predicates or the rules that we define up front. The system enforces the rules. So you don't need every developer to do so, although you obviously rely on them to write the rules themselves.
So, excuse me, Martin has talked a lot about the importance of a solid relational core in implementing the essential state of the system, and he's started us on this journey into our system's essential logic by committing to using Postgres with its views and constraints. But we're only so far along the spectrum, halfway along the logic section. It's not a system yet, unless our customers are willing to log into a PSQL console and get to grips with our data model and check their balance. As Martin has said just now, our data model is perhaps complex. Through banning nulls and updates, we've forced ourselves to thoroughly model time and change, and that means we have a lot of tables. So perhaps even for a very sophisticated customer, well-versed in SQL, we have so many relations through this careful, upfront, future-proof, flexible design that it really would be a nightmare to check your balance or get your tax statement for last year. So now we need to build this stuff for customers and for our operations teams to do their jobs tractably. And it's in this business logic layer that we add back in the access path that COD removed. The data exposed to a customer via mobile is very different to that exposed to fraud personnel in ops. So this business logic, it views and projects a dimension of the relational core from Postgres appropriate to a customer or an operative. And here is where your differing user needs are expressed, and indeed your security model could be implemented. And doing so is a joy owing to the data independence provided by the relational core. So I'm talking about how to survive building and maintaining your essential logic without getting tied up and straying too far over to the right side of the complexity spectrum. And I'm going to draw on the works of Ben Mosley and Peter Marks to help me do it. These guys wrote the awesome Out of the Tar Pit paper in 2006, which I highly recommend everybody reading, if you haven't already. They build on Brooks's complexity dichotomy. And one thing they do quite early on in this paper is they sort of review programming languages, how they relate to the modern software crisis, how they relate to complexity, and they cover object-oriented programming as an example of the imperative style, functional programming and logic programming as the more declarative style. And they say that the latter, logic programming, is really the holy grail for expressing your essential business logic in such a way that it describes what is desired of the system rather than how the system should work. They actually settle on the recommendation of functional programming, though, and I suppose as Haskell developers, that's perhaps unsurprising. So, but hang on, yeah, you use Java. So I want to be clear that the paper, it didn't directly influence engineering at Starling, but it does give us a really good language to talk about software systems, and it explains really well some of the most critical engineering principles that we follow. So yes, our services are written in Java, our business logic, but what is a function anyway? It's a transformation. Some data comes in, some data goes out. Ideally, nothing else happens, no other dependencies wrapped up or hidden within the function, no side effects, no sending an email, no notification, or making a call out to another service over HTTP. Just a domain and a range, nice and simple, like in maths. So we have this distributed system, written with Java, well-known, strongly typed, imperative OOP language, but from like 100 feet up, each one of our services is actually really just a collection of pure functions, or compositions or pipelines of pure functions. Data in through HTTP at the top, transformed in services and written to the data store, or data in from the data store, transformed in services, and up and out as JSON over HTTP. And every step of the pipeline is declarative. The data lives in Postgres. Derived data lives in Postgres too, defined in SQL. And at the bottom of our Java stack is a Java interface annotated with some SQL. Java interfaces and annotations are declarative. SQL is declarative. So now this data is in the form of a immutable object, a Java object, perhaps a mutable collection of Java objects, which may be transformed with functions applied to Java streams. And then off it goes as JSON over the wire. And libraries like Jackson mean that the transformation is cross-cutting and declarative. And libraries like JAX-RS allow us to bind a Java interface to HTTP declaratively. We use REST-easy because it automatically generates HTTP clients from annotated HTTP server interfaces. So there's a ton of awesome declarative stuff out there in Java land. If you keep it stateless, you keep it immutable, and then you stay in the safe space away from the right-hand side of the complexity spectrum. So Ben and Peter, in this paper, they go on to propose the hypothetical architecture called FRP, Functional Relational Programming. Shares an acronym with Functional Reactive Programming, but it's different. They sort of pose this as a solution to the modern software crisis, and it consists of essential state down in the bottom right, this is your relational core, at the heart of the system, essential logic, ways of producing derived data, transforming data like creating views in your RDBMS, executing pure functions. It's part relational, part functional. You need integrity constraints, they're in your DBMS, and there's these things called feeders and observers, interfaces, through which relations are created and you get your data in, interfaces through which your data is projected. And you get your data out to customers, their mobile app, or perhaps to that other reporting system that your boss needs for his daily dose of MI. But learning to classify our systems in terms of this complexity spectrum or diagrams like this one, it means we can start to divide and conquer. And Ben and Peter advise us to avoid and separate. So avoid is what we've spent most of our time so far talking about, stripping away anything essential, stripping it back to only the essential state and behavior. For example, out of the top it says that we should avoid mutable state in our business logic because mutable state is accidental complexity. Avoiding things in general, it means thinking very carefully about which costs we want to pay. Everything that you don't manage to avoid might cost you something. So always question whether now is the right time. When will we see the benefits? Are we doing this for the right reasons? Am I just padding my CV? You're going to come up with so many ideas. You're going to see so many talks. You're going to read lots of blogs and tweets, and you can't do or use them all. At Starling, I think we work really hard to avoid complexity. So some of us take a daily dose of healthy skepticism. Separation. It turns out that we can't really avoid all complexity, accidental or otherwise, and so separation is this technique we can use to reduce the potential cost of taking on useful accidental complexity. When you separate things, you have to wrap up and share cross-cutting concerns to get the benefits of consistency. By wrapping up cross-cutting concerns, expressing them declaratively, and applying them consistently, we're able to think more about what is desired of the system than how it works. And by wrapping up cross-cutting concerns, we make our services homogeneous and consistent. So like at Starling, you probably won't find that one team one day will go off and write a service in Haskell. Both being huge fans of closure, Martin and I, we find this a bit tough actually, but as I say, we work hard at avoiding heterogeneity in our systems. Consistent services also kind of promotes or allows consistent infrastructure, which can then also be automated, declarative, through tools like Terraform. So observers and feeders, these, they're like an instance of separation. They implement separation. And separation isn't really, it's not a new idea, it's been around for a while. It happens on another axis, the separation of read and write. Bertrand Meyer in the 80s coined the term CQS, command, query, separation. And it's about placing reads and write operations in separate methods on your objects. Queries have to be referentially transparent. They must produce no side effects. They must really merely return data. And Greg Young took it a little bit further with command query responsibility segregation, CQRS, wherein writes and reads are placed in separate objects. Separating read and write, it creates space for a range of architectures and patterns, like the option to have multiple read models, granted potentially at a cost of accidental complexity through things like synchronization, the time lag and eventual consistency. But this allows the physical scaling of read and write to occur asymmetrically, which is both realistic and pragmatic. So we've done quite a lot of papers and theory. Now for some examples. Martin's the core banking and databasey kind of guy. In case you hadn't noticed, he's back in a bit, but I'm here right now and I'm the web guy, so here goes. So at Starling we use React. It's a very well-known JavaScript library, often thought of as the view layer for single-page applications. We can define React at a high level in some formal-sounding terms by saying that it encourages developers to write a pure set of functions over the domain of your system state, your business and user state, into the range of the DOM. And you might go on to say that your browser is a function over the domain of the DOM into the range of pixels on your monitor. React, it brings together functional and reactive programming patterns, and it raises the consideration of state to the forefront of your developer's mind by offering you two kinds of data. Props, which are values your component receives from the outside, and state, which your component manages itself. By avoiding state and side effects, by programming in a functional style and using immutable data structures, your entire system gains this property of referential transparency, which is a great aid to informal reasoning. So this is where every expression can be replaced with its value without changing the program's behavior. That's your sort of definition of referential transparency. And what it means is that you have a function foo, and every time you give it 2, and it gives you back 4, and it didn't send you an email. So functional programming, it shortens the brain to code gap. And I think that's more important than anything else when you and your teams are all reading back each other's code, at least 10 times more often than you're writing it. Redux, it's another thing we use at Starling. It's a predictable state container for JavaScript applications, a state management tool, if you will. And it's in no way coupled to React out of the box, but it's very common to use it paired. It has a single global state store which can be an immutable data structure. I think it should be an immutable data structure. It formalizes the change in state through actions which describe a request to change state. It notifies subscribers when the store has changed, and you can only change the store by these things called reducers, which you supply as a pure function of state and an action, and you must yield a new state. So Redux assumes that you won't mutate your state anywhere else other than inside this function, which you have provided as a reducer. So the store is a database. It's more than a database. It's an immutable data structure. If you use an immutable data structure there, then it's a value, right? And that gives you this unparalleled capability in the debugging space. And there are echoes of CQS, like separation here, C, commands. They're like events, but they carry intent, they're immutable, and these are akin to actions in Redux. Q, queries. These are things like selectors or cursors, lenses, and zippers. Any pure functional technique for reintroducing modularity over and navigating your global immutable state, purely without side effects and as declaratively, logically, composably as possible. So React helps us avoid and separate. It forces us to think about values and state, to treat them differently, to handle them explicitly. It separates us from the mutable world of DOM and event handlers. And Redux helps us avoid and separate. It provides this middleware stack in which we can place our side-affecting code and deal with the outside world like network calls, separated from the rest of your otherwise rational, reasonable, pure functional program. We chose React, Redux, and Immutable JS because they each do one thing well. They each stand alone. They compose well with other things that do one thing well. And each of these are simple, and they stay simple when composed together, which gives rise to understandability, this excellent informal reasoning, this impact analysis and debuggability. Things that compose easily are easily pulled back apart, and this gives rise to changeability. These support growth, the growth of your product's complexity, the growth of your teams, the number of committers working in the same space. This is a screenshot of one of the apps I look after. We call it the management portal, and it's built on this web stack. It was simple. We adopted it really early, 4 years ago. It's a simple architecture, and it served the original single engineer, Muggins here, very well. But what I find really pleasing is that it hasn't really changed in 4 years, the architecture. The tools changed a lot. But now we've got like 80, I think it was 96 committers at last count. So back then we had no customers, now we've got over 1 million. Back then we had no operations function, and now we have heading towards 1,000 people on board, most of whom use this application day in, day out to service the needs of our customers, the bank as a business, and of course the regulator. So React, Redux, Immutable.js, can I claim it's an FRP implementation? It's definitely functional programming. It's probably reactive programming, but is it relational? No, not quite, probably not yet. But for many of you out there, and I think perhaps for us in the future, I think the missing piece from this collection of libraries to implement an FRP-like architecture are tools like GraphQL. Through GraphQL, web clients, which for years have been sort of tied to prefabricated REST APIs, they reattain the power to query to achieve data independence. And at Starling, we lay out our sort of homogeneous services as HTTP accessible projections of relational data. And we have cross-functional teams, so together, by and large, this usually results in APIs that actually are fit for purpose. I don't need any more queryability than I already have. Lucky me for now. But GraphQL is very much on the radar, and so is functional relational programming. Yeah.
Thanks. So we've talked a bit about complexity. We've talked about how we model and store data independently of the access path, then add that access path back later elsewhere as projections or functions of this relational core. And Dan's explained a bit about how that applies in his area. I'm going to try and do the same in my area in a sort of view of a sort of hypothetical ledger that is pretty close to what we do. And hopefully show along the way a little bit of the accidental complexity you might find in our system. As I say, the data models and everything, I've just sketched them out there. In no way bear a resemblance particularly to what we run in production or anything. So a bank really is just an accounting machine. So we'll start by just thinking a little bit about what a business's accounts really are. In the language we've covered so far, you can think of them as really a projection of all of that business's financially impacting data, a function, a sort of function that takes as input all of that historically modeled, detailed relations that we came up with in front of the whiteboard. And it transforms them into a simple data structure. I've drawn some T accounts, which is what you draw on whiteboards with finance departments when you're building a bank. We've got debits and credits made as postings into ledger accounts. We group those postings into sets called journals, which are the numbers, joining the postings together. The sum of those add up to 0, so the ledger as a whole always adds up to 0, which apparently is quite important. And then a ledger is immutable, which is also reasonably important. Though you can and you do post immutable adjustments by distinguishing between the posted timestamp when the event landed in the ledger from the value timestamp. Now, assuming that you've stored enough data in your data model, you could actually kind of think of a company's accounts as little more than a query over these really diverse set of financially significant events that flow through our system. That essential state of our system expressed through a set of facts or relations. Transaction settlement messages from MasterCard or Visa payment networks, in and outbound messages representing bank transfers in faster payment service or SEPA. And in each case, we store lots and lots of detail so that we can keep track of everything from an operational perspective. We can switch a card transaction in the feed from pending to settled. We know when we need to settle with a particular payment network for how much, which customer payments have been settled as part of that batch, and so on. But the finance team doesn't care about all that detail. Their domain looks at the business from 30,000 feet up. And so to represent these relations in the accounts, they all first need to be transformed so that they share the same data type. So we go from this diverse, detailed, lots of individual representations into this simple, generic, unified data model in the ledger. We're purposely throwing away the detail in order to see the wood for the trees. Now, if we're talking essential versus accidental complexity, then the way I've described that the ledger is actually on the accidental side. Because you could actually construct this crazy query. You could represent the ledger postings from this underlying complex data model. It would be a bit of a beast, of course, involving the union of dozens of different relations, all projected into these ledger postings. And it would be pretty unmaintainable. It would be represented in code. So you would run the very real risk that a future change to that code, a bug that you might introduce, could rewrite history, and you violate this property of immutability. And so at this point, we start to think about denormalization. We're going to store the ledger tables effectively as simplified copies of those raw underlying facts. And for the sake of illustration, I've drawn out some logical data model, what it might look like. It's obviously a pretty basic and weak model, though I was trying to illustrate really that is, I've got a sort of payments domain, card domain, treasury, and FX, lots and lots of complicated detail, and everything joins in the middle to this simple ledger model in the center. And you've all been to the microservices talks here at QCon, I'm sure, this year and for the last many years. And so I won't spend too much time talking about the why, but although I've drawn this as I drew it as a sort of monolithic, big, system-wide domain, if you imagine it, of hundreds of tables all joining into the ledger, in reality, we have good reason to break our system up. And we break it up into about 30-odd services. There's an element of Conway's law here, allowing teams to own their services, to control their releases. There's also an element of domain-driven design. So by allowing the domains of the system to diverge and to grow independently based on the expertise of the particular team owning that system. But why do we land on about 30 services? So where does that granularity come from? Well, firstly, we follow a strategy called self-contained systems. If you're going to break the bank up into many different services, we feel that they should be able to run those services independently of each other. And we're trying to reduce the blast radius of errors here to stop a problem in one service taking down others. And that means minimizing synchronous calls between separate services. If each of those services is allowed to talk to a few others, then you're quickly in danger of building this distributed monolith, this network of expensive and brittle calls in which any error can quickly cascade throughout the system. And using self-contained systems also means that each service has its own database. And we've talked repeatedly about the importance of relational modeling. Now, I've drawn some teal boxes here, which are supposed to represent some imaginary systems, and each of a self-contained system that is dividing my domain up into many different services, each with its own database. Now I've gone and cut my database into loads of parts. I can't write nice queries across them. I can't enforce constraints across those records. So what's going on? What have I done? Well, of course, it's all about trade-offs. To gain the benefit in one area, you pay the price elsewhere. We want to gain the benefits of self-contained systems, of these multiple services, and we give up a bit of that simple, consistent modeling. But we don't want to go all the way. We don't want to give it all up. There's definitely a role for reconciliation, but as a bank, consistency is obviously really important to us. So, given what I've described, how do we go about maintaining that consistency in the face of this destruction of our lovely, neat model? So I've drawn up here my service boundaries going right through the middle of some entities. And those entities are effectively shared across services. So each piece of data in the system has a home. It is owned by one part of the system as its primary owner. So we might have a finance message being something related to card and cards domain. You have a payment perhaps created by the payment service, something to do with FX down at the bottom, right? In each of those domains, you have a rich set of historically modeled events, but one of them is going to be the one that is pushed across into the ledger. And we see this as a sort of form of event sourcing. From its home in one service, data is pushed into other services where it becomes joined into the relational model of that service. We've reduced the surface area of how these different services connect. Detailed model on one side, simplified domain-specific model within the particular ledger service that I might have drawn here. And we're pushing data rather than doing remote procedure call or anything like that, because we want to minimize the amount of transformation that happens across the data, across this barrier, this bridge. We might send a subset of the columns or filter it out, but we're really trying to avoid having a complicated dependency on some piece of code that happens to execute, that is versioned in GitHub and changes. Otherwise, I won't know, well, what's the representation of this particular card transaction on the other side. So this part of the system we've described in the past as a ditto architecture, do idempotent things to others. And on the consumer side of that, we ensure that the receiving service, here the ledger, the endpoints receiving those messages are idempotent. We can replay the message as many times as we like. It will land once. So that means you can handle errors by repeatedly replaying. You just keep throwing it over the fence, and when you know it's stuck, you stop trying. On the producer side, we've gone through a few different iterations and implementations of this, and it's definitely, as I said, to show a little bit of the accidental complexity, we've sort of narrowed it to this thin channel, or hopefully thin channel, across these entities being pushed through the system. But the implementation we use now is based on Postgres, on a feature called PG Notify, which allows, where Postgres is notifying our Java services through the JDBC connection when a record is inserted into the database. So that means that in the same database transaction, we're able to commit a piece of data, a record representing a transaction, together with another record representing the command of pushing that piece of data into another service. And so we can delegate that consistency of pushing the data across the boundary to a Postgres transaction management. We don't need to worry about complicated two-phase commits or expensive distributed locking or synchronization technology. And it's worked pretty well for us. Though it's definitely, as I say, a part of the system that will continue to evolve and improve. I'd like for it to be much more declarative, so there's less pushing, more declaring that I need to subscribe to a particular type of event. So why don't you just use Kafka, I hear you ask? Well, for a start, at the beginning, we were unwilling to take on what we considered this inessential complexity early on. We would sacrifice a lot of developer productivity, requiring everyone to run this complex piece of technology, as well as needing to build up the expertise in production. And we had so much to do delivering features, getting stuff done for the business. And we also couldn't see immediately what benefit it would bring, because we still had the worry about the consistency guarantees. We still got to make sure that the data crosses barrier, and so we'd still have to implement that stuff I described before. Kafka obviously improving rapidly. They've got exactly one semantics and so on. I'm sure lots of our concerns have been addressed, and I can sort of see a use case where if we increase the number of consumers that we were pushing data to, or we had a use case where we were regularly replaying large swathes of the data, then we could introduce the broker in the middle to take the load off the source system. But a better option for us might actually be logical replication, which is a Postgres feature. And Postgres actually exposes the write-ahead log within the database. And that's the log of changes that the database records as it's storing the data. And you're able to effectively subscribe to that and also specify the format, the format in which you consume that piece of data. The client can be another Postgres database, as in traditional replication, but it can also be a service. You can write a Java client to consume this write-ahead log, effectively, or the logical replication log. And so that allows us to turn this place-orientated data store into an event producer. And it's effectively the solution I spent a bit of time describing before. We get to keep our consistency guarantees and the transaction boundaries with a lot less moving parts than running a big separate cluster. So as I say, this architecture will continue to evolve over time. So you've seen a bit of the theory we presented at the start, how it translates into real-life engineering at Starling, in the web, in the vault where I live. And we start to wrap things up now by thinking a little bit about Starling's engineering principles and what pragmatism means to us. So on Greg's track today, you're going to see quite a few fintechs all solving really similar problems. But we've all had very, very different journeys. So why is that? Well, software engineering really is, no surprise, a long series of trade-offs. There's no single right answer, and the questions we're asking are changing every day. So we're really engaged as engineers in the art of compromise, the orchestration of compromise, lots and lots of small decisions which in sum define the journey that we take. But if we exist in this state of constant compromise, what is it that stops us undertaking some myopic random walk through this forest of options, of opportunities, of choices? Well, the compromises we make are through decisions, and those decisions are hopefully grounded on a principled foundation. And it's those principles which give purpose and they give direction to the compromises we make, and thereby determine the system that we actually end up building.
Rampant pragmatism. That's what we call the talk, but what is pragmatism? So one definition is that it's an approach that evaluates theories or beliefs in terms of the success of their practical application. So your theory and experience inform what you believe, and then you can apply your beliefs practically. And then we experience building systems, running systems, being on call for systems, smashing your mobile phone when PagerDuty rings. We evaluate it constantly. Right? We figure out what to keep, what to tweak, what to throw away. So pragmatism is a feedback loop, right? It's navigating the world with your eyes open and moving deliberately. And what we call architecture as software engineers is really just the result of some people placing some bets on what they think needs to be easy to change later and what doesn't. So we did this 4 years ago. We started with a blank canvas. And we made up some principles and we made up some high-level aims that we thought were going to help us win at life. We said things like developers must love the experience of building this thing. And things like problems in production must not affect the entire system. Their blast radius must be limited. And so you place these bets and you close some stuff off and you leave some stuff open. You mix and pour some concrete over there. You place some lightweight, eco-friendly modular furniture made out of hemp over there. But for sure, for us as a startup back then with a small team, but big ideas, data was always going to change. And as a bank looking after your money and regulated to the highest degree in the finance world, we knew it had to add up. It has to be consistent. So we placed a couple of bets to allow our data to change easily without compromising consistency. Obviously, we chose a relational model as opposed to a graph or document or object model. And we place emphasis on the acid properties of transactions within our services. And we think these were good bets. However, we learned a few things about betting along the way. So a few words of warning, pieces of advice. Be aware that these bets, decisions and compromises you might make in the spirit of pragmatism, they can produce artifacts which have gravity and momentum. They can be big, they could last. In other words, concrete is a little bit harder to break up than hemp. So be guided by principles, explicit or implicit, and I'll talk more about ours in a moment. Be guided by experience, or the experienced among you, and place your bets on what will or will not be expensive to change. So how can we help ourselves make good bets? And I think that bets plus principles yields an architecture. Let's say you've got a choice, option A and option B. You can put your spectacles on and perhaps become less myopic and reduce the risk of this decision by testing A and B against your principles. You can ask how A affects developer productivity, what about B? So these principles make your bets less of a gamble. So what other principles have we established at Starling? What other bets did we place as engineers? Well, first and foremost, we optimize for developer productivity. I can run the whole thing on my laptop. Granted, it's a beast of a laptop, but I can do that, and I can run a raft of simulators at the same time representing external dependencies like the faster payments network or the Swift network, such like that. Now, I've never experienced this quite like this before anywhere else before joining Starling. Not to this extent, not to this scale, and not to this effect. I genuinely believe that this This on its own, this principle of optimizing for developer productivity, is what allowed us to basically build this and go live in about a year with a handful of engineers. And since then, while we've been growing rapidly, we build and empower cross-functional teams, requiring of them minimal process. And I think these things keep us focused, moving fast and unhampered. So we also strive for understandability, or perhaps better, changeability, or even better, low-risk changeability. We have these 30 services. They're written in Java, and they're in a mono-repo. So I get to open them in my IDE all in one go, press Control-Alt-H, and see how the data flows through my entire system, both within a service and across a network boundary into another service. And this yields easy static analysis and informal reasoning, and these help me to make the right kind of change. We also preach a little bit, thou shalt write code for future you, your colleague to your left, who you respect, Martin, and the guy who's on call. So in practice, this looks like simple stuff that I hope we all know about already. Things like changing your stuff incrementally so that you have small, short-lived branches and tractable PRs. And then since your feature is going to be spread out across PRs, engage a few people in the sort of medium-term review of these features across those PRs. Be kind, communicate, do unto others as you'd have them do unto you. Really simple stuff. Simplicity, consistency. We believe in these two things. And all of our stateless services are composed of just a handful of common tokens. They all communicate externally and internally through HTTP APIs. They may or may not have daemon background processes or scheduled jobs, and they all persist state to their own transactional relational data store. Homogeneous services, homogeneous infrastructure, and we sort of wrap up cross-cutting concerns and apply them consistently across those services. We limit dependencies in two ways, both within our programming language, so our POM file, our POM XML, yes, we still use Maven. It doesn't have thousands and thousands of dependencies, and we carefully manage the dependencies between our services too. Why all this care, or restriction even? Because simple and consistent is understandable and changeable. When we were a young and small team, we could all do everything. We could switch and pivot and keep pace. We had a lot of finance and banking domain to learn, and that was hard enough. The development had to be fast. We had to be able to take it for granted. And while we've been growing, this has also been very useful for onboarding new engineers, getting them up to speed quickly.
So hopefully that has given you a bit of an overview of how we interpret pragmatism at Starling Bank. I'm certain that we will continue to grow and change, and we will move further along that spectrum of complexity, right? We'll take on more complicated tools, we'll hire teams to manage them, we'll continue to denormalize our data, and I can't wait to tell my boss that I desperately need to build a distributed database for a start. But we will continue to focus on the essential, on data, on our customers, and on delivery. We're, as an industry, quite obsessed with accidental complexity. And I like shiny tools as much as the next person, but you really do have to think carefully about the costs of the choices you're making and whether they're appropriate in your context. Don't let some sense of tech status anxiety cause you to make choices that are not appropriate to your business now. Not many companies actually have the tech challenges of a Google or a Facebook, and I bet that you would not be willing to accept a lot of the compromises that they've been perfectly happy to make. But know also when to take that leap of faith, tackle the next big problem, address the bit of tech debt that you've built up. By the time you get to that point, you'll have all the context to make the decision and to do the right thing. So we won't stand up here and tell you particularly what choices are best for you. All the talks are here, you can watch them yourselves, weigh up the costs of the bets that you are making. And as Vicky Boyka says, you may not actually need Kafka or Kubernetes right now. Perhaps the price is too high. And then again, they're powerful, they're exciting technologies, so maybe it's not, and you do. You decide. So thanks very much. That is all we have for you. Have a look at our recruitment page if you're interested in the sound of any of this. We did a lot of research on whilst figuring out this talk. So if you download the slides, a bunch of interesting papers that some of which we've mentioned, some of which we didn't even get to mention. So thank you very much.